Welcome everybody. My name is Philippe Michel and I will be moderating this afternoon session in room 1. Our first talk today lies at the intersection of section 3, number theory, and section 9, dynamics, and it is given by Joseph Silverman. Joseph Silverman is professor at Brown University, and before he obtained his PhD at Harvard under the supervision of John Tate. He has been Moore instructor at MIT, then professor at Boston University until he moved to Brown. Joseph has collected a number of honors, including a Sloan Fellowship, a Guggenheim Fellowship, and he was elected a Fellow of the American Mathematical Society. Joseph has a wide range of interests connected to number theory, including algebraic number theory, arithmetic and Diophantine geometry, and also cryptography. For several years, Joseph has been a driving force in the development of arithmetic dynamics, and today he will give us an overview of this field.
Thank you. Thank you all for coming. I want to thank ICERM for sponsoring this event. As Brendan said, what I'd like to talk about today is to give a survey of this field called arithmetic dynamics, which is a comparatively young field, and it's a combination of three quite old fields of mathematics, the first two of which really date back a very long way, number theory and algebraic geometry, which have been linked to some extent for a long time, but certainly for the last century, they've been very closely linked in the field called arithmetic geometry, where one studies rational points on algebraic varieties. And then I want to throw into the mix the field of dynamical systems. And if you combine these three, you get what is called arithmetic dynamics. So let me just mention briefly what each of these three pieces are and then how we fit them together. So first, number theory, which dates back to antiquity and beyond, is the study of properties of integers, or maybe more generally rational numbers. Algebraic geometry, also a centuries-old field, is the study of solutions to systems of polynomial equations. And discrete dynamical systems, also a very old subject, is when you iterate a function and study orbits of where points go. So, combining those three, arithmetic dynamics becomes the study of the number theoretic properties of orbits of rational numbers when you apply a function many times. So in this talk, I want to concentrate on arithmetic dynamics over the rationals, or more generally, over finite extensions of the rationals, although there are many other parts of arithmetic dynamics, especially over the p-adics and over finite fields. And the primary focus will be on analogs in dynamics of famous theorems or conjectures in arithmetic geometry. And again, there are a lot of possible topics to choose from, so at least in my write-up for the ICM proceedings, I decided just to concentrate on 5 of them, which you can see here, which I won't actually read, but they'll be on the next slide. However, when I started writing up this talk, I realized even getting through 5 topics in 45 minutes would be quite a rush, so I'm just going to do 3 of them in a bit more detail. So these are the 3 that I'll talk about: dynamical uniform boundedness, dynamical complexity versus arithmetic complexity, and dynamical moduli spaces. But before getting to any of the topics, I need a few definitions. So what is a discrete dynamical system? Well, completely abstractly, it's simply a set x and a function from x to itself. Because once I have that set up, I can iterate f, do f composed with f, and I'll write f to the n for the nth iterate of the function f. And what we're usually interested in is what happens to points in x when we repeatedly apply the map f. So the forward F orbit of a point x is just f to the n of x, all the iterates of f applied to x. Some people include x in the orbit, some people don't. I will, though it won't really matter. Of particular interest are points which return to themselves. So after you apply f a certain number of times, you get back to where you started. And those are called the periodic points, and the smallest iterate that gets you back to where you started is called the exact period. And slightly more generally are the f pre-periodic points. Those are the points that after you move along, at some point you hit a periodic point. So a periodic point makes a loop. A pre-periodic point would have a tail and then a loop. So as I said at the beginning, I want to talk about dynamical analogs of results and conjectures in arithmetic geometry. And to some extent, we can do that using the following dictionary. So in the arithmetic geometry side, one looks at rational points or integral points on varieties. In other words, solutions to polynomial equations in rational numbers or integers. And I'll translate that to looking at rational and integral points in orbits. An important subject in arithmetic geometry, well, people study abelian varieties. These are varieties that have a group structure. And one looks at the torsion points, the points of finite order for the group structure. And those translate into talking about periodic or pre-periodic points of maps. One also studies varieties that have special structures. And as an example, abelian varieties with what's called complex multiplication. So it's a special class of abelian varieties. And something somewhat analogous to that would be special classes of functions that we're going to iterate, for example, what are known as post-critically finite functions. These are maps on P1 whose critical points are all pre-periodic. Now, the first analogy at the top of this slide is very natural. Right? Rational and integral solutions to polynomial equations, rational and integral points in orbits. The second one's pretty natural also, because if you're talking about a torsion point in a group, a point of finite order, that's equivalent to the element of the group being pre-periodic, say, for the squaring map, x goes to x squared. The third analogy is a little more tenuous. And certainly, there's room for improvement on it. It's basically based on the fact that if you look at the moduli space of abelian varieties versus the moduli space of rational maps on P1, there are these special marked points that have algebraic coordinates. And they're characterized by the underlying object having some special property. So work in the last decade or so by a number of people has provided some justification for the third analogy, but there's still a lot of vagueness there, especially if you try to go to higher dimensional dynamics. Okay, topic number one, uniform boundedness. So let me start with a theorem in arithmetic geometry, a very famous theorem of Barry Mazur's from the 1970s that was extended by Cavieini and Morel. And Mazur's theorem says if you take an elliptic curve over Q, so it has a group structure and you can look at the Q rational points, it's known that the points of finite order form a finite subgroup. And Mazur's theorem says that that finite subgroup is bounded independently of the curve. And in fact, he gets a very sharp bound. There are no more than 16 points of finite order defined over Q. And I actually don't know who made this first, so I'll just call it a folklore conjecture, that the same thing should be true for abelian varieties. That an abelian variety over Q, the torsion subgroup defined over Q, should have size bounded by a constant that's essentially independent of the abelian variety, just depends on its dimension. So the dictionary on the previous slide says that we should translate torsion points on abelian varieties into pre-periodic points on dynamical systems. And this leads to the uniform boundedness conjecture. which Patrick Morton and I formulated for projective space. It says that if you look at n-dimensional projective space and look at maps f of degree at least 2, so degree d, say, and the map is given by polynomials with rational coefficients, then we can look at the periodic points or preperiodic points that have rational coordinates, and the number of preperiodic points with rational coordinates should be bounded by a constant that's basically independent of the map. Just depends on the dimension of the space and the degree of the map. This conjecture remains far out of reach and seems to lie fairly deep. Just to give an idea maybe of its depth, the very special case of taking P1, the projective line, and taking maps of degree 4, if you knew this uniform boundedness conjecture, you'd get a version of Mazur's theorem. Maybe not with 16, but with a uniform bound. And van Cruden showed that if you knew this uniform boundedness conjecture for all projective spaces, then it would also imply the uniform boundedness conjecture for abelian varieties on the previous slide. Okay, so since the conjecture seems inaccessible, as mathematicians are wont to do, we'll look at a special case. So let's look at the simplest possible collection of functions that might be interesting. The simplest functions would probably be linear, but that's maybe too easy. In dynamics, people usually start with quadratics, and in this case, quadratic polynomials. So we'll look at the collection of polynomials x squared plus c, where c is a rational number. And the question becomes, if I give you an n, can you find a rational number c and a rational starting point b, so that if I start with b and I iterate x squared plus c on it and get this orbit, do you get a cycle of size n? And for small n's, it's pretty easy to see you can do this. Here are the first few. So if you want a fixed point, look at x squared and 0 is fixed. If you want a cycle of size 2, you can take x squared minus 1. And if you start with 0, you go to minus 1, and minus 1 goes back to 0. You can get a cycle of size 3. It's a little more work to find it, but x squared plus 29 over 16, if you start at minus a quarter, you get that triangle. Minus a quarter goes to minus 7/4, goes to 5/4, goes back where you started. All right, that settles n up to 3 for quadratics. What about n4 or bigger? Well, there's been some progress on this. Patrick Morton showed that you cannot get n equals 4. Flynn, Poonen, and Schaefer, about a decade later, showed you can't get n equals 5. Not bad. Michael Stoll showed that you can't get n equals 6, although it is conditional. He needed to know a certain abelian variety had a certain rank, and we can't actually compute it, so he needed to use Birch-Swinert and Dyer. Still pretty good. And recently, Nicole Looper showed that if you assume something like the ABC conjecture, but with more variables, then in fact there is an n naught, so that you can't get any periodic cycles bigger than n naught. So that would be uniform boundedness for quadratic polynomials, but assuming this very strong conjecture. So let me give you a word or two about how, well, at least how all of the results on the previous slide, except for Looper's, are proven. She used a rather different approach. The idea is that there's a curve whose points characterize the solutions we're looking for. So there's this dynamical modular curve, x1 of n, that classifies pairs of points, b comma c, where b gives a cycle of exact size n for x squared plus c. It's very much analogous to the classical elliptic modular curves, which classify elliptic curves with a point of order n. which in fact is the starting point of the proof of Mazur's theorem. So this reduces the problem of sort of looking at the dynamics to, well, I have a curve, I just want to find all the rational points on it, and in this case, prove that there are no non-cuspidal rational points if n is 4 or bigger, say, or for any particular n. Unfortunately, a key tool that Mazur uses to prove his uniform boundedness theorem for all n is the theory of Hecke correspondences. So on these elliptic modular curves, they're what are called correspondences that turn out to give a lot of structure and are very helpful. And there does not appear to be an analogous collection of correspondences on the dynamical modular curves. And in fact, for those who know the theory a little bit, the dynamical modular curves, their Jacobians tend to be simple. They don't break up into pieces at all. Okay. So, topic number 2 that I wanted to talk about was complexity in a dynamical setting, in a number theoretic setting. And I'm going to take a very informal approach of what I mean by complexity. It's sort of a computer science type approach, but very vague in some sense. So I'll define the complexity of an object, whatever an object is. There'll be several different kinds of objects. To be the number of units you need to describe it. It could be the number of bits or the number of coefficients or something like that. And I'll call it h of O, well, at least on this slide, because number theorists usually call this a height. But so a couple examples should make it fairly clear what I mean without having to go into really formal definitions. So if you have a rational number, P over Q in lowest terms, its complexity is the number of bits you need to store it up to a scaling factor. So it'd be the logarithm of the larger of the numerator and the denominator. Or if you have a rational function, so a ratio of polynomials, then its complexity would be basically how many coefficients there are, which up to a scaling factor is the larger of the degrees of the numerator and the denominator. If you could take the sum of the degrees if you prefer, it's just a scaling factor of 2. Okay. And the goal is going to be, the objects are going to be the points in an orbit, for example, or the iterates of a map. And we want to know how fast complexity grows when one iterates. So the first topic that I want to look at here is the more geometric dynamical setting. So I'll start with just a map from projective space to itself that's given by a whole bunch of polynomials, say homogeneous polynomials of degree d with no common factors. Okay? And in that case, again, up to a scaling factor roughly, the complexity of f is simply its degree, which will give you a bound on how many coefficients all those f's have. Okay? But a crucial thing to note here is that when we write a map from projective space to itself like this, we want to make sure the polynomials don't have any common factors, because if they do, we're working projectively, so they cancel out. So the f0 through fn, there's no polynomial that divides all of them. But interestingly, if you iterate one of these maps, suddenly the polynomials you get in the iterates may have common factors that cancel out. So the degree of the nth iterate may actually be strictly smaller than what you'd expect, which is d to the n. Okay. And here's usually the first example everyone shows to demonstrate this fun example. So here I'm taking a map from the projective plane to itself. So I have x0, x1, x2, and it goes to the triple x1, x2, x0, x1, x2 squared. And a fun exercise is if you iterate this, the degree of the nth iterate's actually a Fibonacci number. It's the n plus second Fibonacci number. So what we want to look at is how fast the degree grows keeping in mind it might grow slower than d to the n. So we take the degree of the nth iterate and see to what extent it's growing exponentially. So we take the nth root of that and let n go to infinity. And that limit's called the dynamical degree. And one can show that it converges. And the intuition on this is, I mean, if you move the nth root to the other side there and forget about the limit, the degree of the nth iterate of the function is roughly the dynamical degree to the nth power. So if the dynamical degree is 1, for example, the growth is not exponential. If it's bigger than 1, the growth is exponential. And there's a real dichotomy in the dynamics between those two cases. So for example, that map on the previous slide where the degree of the nth iterate was a Fibonacci number, if you take the nth root and take the limit, you get the golden ratio. So for example, these dynamical degrees may be irrational. And there was a long-standing conjecture, though, that they're always roots of polynomials. They were first studied in the 1990s by a number of people, dynamicists mostly, partly because there's a relation between this and the entropy of the map. And in fact, the dynamical degree is often called the algebraic entropy, or I guess it's the log of the algebraic entropy. And as I just said, there was this long-standing conjecture about what these dynamical degrees look like, and in fact, it's wrong. So over the last couple of years, I did want to say, this is not the most general result in their papers, but what they proved is that for any n at least 3, there is not simply a rational map on projective n space, but a birational map, meaning it has a rational inverse even, whose dynamical degree is a transcendental number. And they also proved the same thing for n equals 2, but there you can't get a birational map. So for the rest of the discussion of complexity, I'm going to want to talk about more general varieties than projective space. So I figured I'd better put up the definition of dynamical degree in general, but it's pretty much the same. If you have a dominant rational map from a variety x to itself, you take the nth iterate and look at its degree. Degree now is relative to an ample line bundle, but it actually doesn't matter which one you take. Take the nth root, take the limit. So very similar. Okay, that was sort of dynamical geometric complexity of maps. Now I want to talk about number theoretic complexity. So I mentioned the complexity of a rational number is just sort of the log of the maximum of the numerator and the denominator. A little more generally, if you have a point in projective space defined over Q, it has projective coordinates where all the coordinates are integers and they don't have any common factor. And in that case, we'll define the height of P, or the complexity of P, to be the maximum of the coordinates, but I take logarithm because I kind of want to count how many bits they take up. And more generally, one can do this for any variety and any number field. So a height function relative to an ample divisor on the k rational points of a variety is essentially a measure of how many bits you need to describe the point P up to a scaling factor. And this can all be done much more precisely, and there are very interesting height functions, but this will be plenty for what we need. Because even with this, one has the question of, if I have a map from x to itself, and I have a point, how fast does the arithmetic complexity grow as you iterate the map f and apply it to the point P? And there's one little glitch, that a rational map is actually not defined everywhere. there may be a subvariety of indeterminacy. So I'll define x sub f to be the points where all of the iterates of the map are well defined. It's actually known that there are a lot of such points, although, well, over C, that's not so hard. Over number fields, it's more difficult. But anyway, the theorems I'm going to say are not vacuous because these sets are not empty. So if we have a point whose forward orbit is well defined, then I'll define the arithmetic degree very similar to the dynamical degree, but I'll just substitute taking the heights of the points instead of the degrees of the maps. So we take the nth iterate of f, apply it to the point. Since you can have 0 there, I put in the max with 1. You take the nth root and let n go to infinity. And this is a natural measure sort of the average arithmetic complexity of the points in the orbit. Unfortunately, we don't even know that this limit always exists. So in order to have theorems that don't have to put in the assumption this exists, I'm going to define the upper arithmetic degree to be the lim sup rather than the limit. And that's actually easy to show that that does exist because you can show that the sequence of heights of the nth iterates of the point is bounded above. So we have these two measures of complexity. If I have a map and I have a point, the map itself has its complexity of its iterates, and then we have the complexity of the points in the orbit. And a theorem that Shu Kawaguchi and I proved for morphisms, those are maps that are defined everywhere, so don't have indeterminacy. And Matsuzawa proved it in general, is that the upper arithmetic degree is bounded above by the dynamical degree. And what this really says is that if you look at the number theoretic complexity of a point as it's moving around, it can never exceed the dynamical complexity of the map itself. This, of course, raises a very natural question of when are they equal? Which points have maximal arithmetic complexity? And there, I wish I could say that Kawaguchi and I have proven a theorem, but we at least made a conjecture. We conjectured that if the orbit is dense, so big orbit implies that the arithmetic complexity is as large as possible. So maximal dynamical geometric complexity in terms of the orbit being dense implies maximal number theoretic complexity, that the arithmetic degree is as large as possible. There's been quite a lot of work on this conjecture over the last decade or so, using all sorts of tools ranging from linear forms and logs to canonical heights, the minimal model program, and other tools that I don't really understand. So here are some known cases by a whole bunch of authors. I decided not to put all the authors' names on the slide, so I apologize to all the people who proved these things. They are in the article in the proceedings, but there's a whole bunch. So, but it's a lot of special cases, and it feels like we don't actually have an approach that might yield a general theorem. So it's known for basically maps of semi-abelian varieties that preserve the group structure in some sense. It's known for maps of projective surfaces. It's known for maps in projective space that are extensions of what are called regular affine automorphisms, so nice automorphisms of affine space. It's known for various non-invertible endomorphisms of threefolds of Kodaira dimension 0. A lot of words there, meaning these are special cases, and these are hard theorems, a lot of them. Many of them use the minimal model program. And also for what are known as int-amplified endomorphisms. These are maps which have, for which there's a divisor with some very special property. Okay, so since every talk is supposed to least sketch a proof. I'm going to sketch very quickly in one slide, basically, sketch the proof that Kawaguchi and I did for homomorphisms of abelian varieties. So we'll take an abelian variety. F will be a homomorphism, which is called an isogeny. We'll take a rational point. And I'll prove the contrapositive of the conjecture, namely, if the arithmetic degree is strictly smaller than the dynamical degree, then the orbit is not Zariski dense. And what we do is we look at the action of the map F on the Néron-Savary group tensor R, which is just a real vector space. Well, that should be F lower star, by the way. No, actually, it should be F upper star. In any case, we have a linear transformation of a finite dimensional real vector space. We can look at eigenvalues and eigenvectors. So in this case, we look at an eigenvector, really an eigendivisor class, that has the largest among the various eigenvalues, and one can show that that eigenvalue is in fact the dynamical degree. Then the assumption on the arithmetic degree that it's strictly smaller than delta sub f shows pretty directly that the canonical height of the point is 0 relative to this eigendivisor class, d sub f. If d sub f, the divisor, was ample, that would imply the point was a torsion point, and we'd basically be done. But in general, that's not true. What is known is that d sub f is what's called numerically effective, which means it's on the boundary of the amplicone. So it's just an epsilon away from being where we want. And then the heart of the proof is this lemma that says if you have a non-zero numerically effective divisor class, then the points with canonical height 0 for that class are actually translates by a torsion point of a proper abelian subvariety. So an abelian subvariety that's not the entire abelian variety. And the proof of this uses a bunch of algebraic geometry. In our case, we have this special divisor, this eigendivisor d sub f, and one can show that f maps this special subvariety to itself, and then at the bottom of the slide there, we're done with the theorem. Arithmetic degree less than dynamical degree implies the whole orbit is contained in translates of this proper subvariety, which is not Zariski dense. All right, excellent. On to topic number 3, which I guess this is going fairly quickly. Maybe I should have just done 2 topics. Anyway, the goal of looking at moduli spaces in general is you have a bunch of objects and you want a space that classifies them up to isomorphism. So in this case, we're going to classify dynamical systems. So first I start with my objects, which are the degree D morphisms, maps that are well-defined everywhere, from projective n space to itself. I'll call that end sub dn. And a map like that is specified by a whole bunch of homogeneous polynomials of degree D. And if I just look at f as being specified by all the coefficients of all those polynomials, I can use those coefficients just as the coordinates of a point in some huge projective space. And it turns out that there's a hypersurface it avoids. Anyway, so I can identify this collection of maps with an affine subvariety of some huge projective space, just by looking at the coordinates of the polynomials. However, that's sort of too big a set. I'd like to identify 2 different dynamical systems if they're essentially the same, by which I mean if they're the same up to changing coordinates in projective space. Because if I change coordinates, I get essentially the same behavior. And the way to do that is we look at automorphisms of projective space, which are just given by n+1 by n+1 matrices. And I take a map F and I conjugate it by one of these automorphisms. So phi inverse composed with F composed with phi. And this is the correct identification to take for dynamics because this identification commutes with iteration, right? The nth iterate of the conjugate of f is the conjugate of the nth iterate of f. So they really do have the same dynamics, f and its conjugate. And we look at the quotient of the space of maps modulo this action. And I'll call that m sub n d. And it corresponds to degree d dynamical systems on projective n space up to change of coordinates. And these are the spaces we'd like to understand geometrically for studying, say, complex dynamics, and arithmetically, because the rational points in varieties like this will tell us about maps defined over Q or over number fields. Okay, so that quotient at the top of the slide in yellow is simply just an abstract set. Well, no, it's a variety, but I mod it out by a group, so the quotient is an abstract set in some sense. But in fact, these quotients have pretty nice structure. So Milner showed over C that the quotient has a natural structure as a complex orbifold. And then a number of people, I mean, I did this for n equals 1, and then a number of people generalized it to higher dimensional n, that the quotient exists sort of as nice as you'd like. It's a scheme over Z in the sense of geometric invariant theory. In particular, if those words don't mean much, that's fine. It means that these quotients exist as nice algebraic varieties defined over fields of any characteristic. So you can do characteristic P dynamics as well as complex dynamics with them. Beyond that, we don't know that much about these spaces. There are a lot of open questions. However, for small degrees and dimensions, we do know something. So degree 2 maps on P1, the moduli space turns out just to be isomorphic to the affine plane with a natural compactification of P2. And more generally, maps on P1 of any degree, the moduli space, it's not affine, but it is birational to a projective space. In other words, there's a rational covering map with a rational inverse. That was proven by Alan Levy. But that's, again, just for maps on P1. For maps on Pn, for n bigger than 1, we still don't know. It's an open question. And actually, I don't think there's even a consensus as to whether these spaces are rational varieties or not. How might one get one's hands on these spaces? Well, the way one studies moduli spaces frequently is you look for functions on those spaces. For abelian varieties, the moduli spaces, one looks at theta functions. Here, we don't have anything really analogous to theta functions, but there's something called multiplier functions. So what's that? Well, if you take a point of period n for your map, this is where the star is supposed to be lower star, then f to the n fixes the point P, so it maps the tangent space at P to itself. The tangent space is a vector space, f to the n lower star is a linear transformation, so you get eigenvalues. And you can just look at the eigenvalues of that map, or the eigenvalues of the Jacobian matrix. It's fairly elementary to define. And if we take that set of multipliers, it turns out that it's the same for f and for f conjugated by an automorphism. Therefore, these multipliers are well defined for points in the moduli space. And if we take symmetric functions of them to actually get nice functions in the moduli space, you get a multiplier map, which uses the given a map F, you take all the multipliers of all its points of exact order n, and you can use that to define this map into affine space. And a very beautiful theorem of Crick-McMullen's is that, at least for maps of P1, if you fix the degree of the maps D and look at periodic points of a high enough period, you get a finite to 1 map into affine space. It's actually, it's never really injective. And what I said isn't actually true. When D is a square, there's this curve that gets crunched down to a point, but it's morally true that it's finite to 1. It would be very interesting to prove or disprove analogous things for maps in higher dimensional projective spaces, because the multiplier maps are well defined there, but that's an open question. So in the last couple minutes, I want to take these moduli spaces and add what's called level structure, which again is a standard thing to do in algebraic geometry. We could look at the moduli space of all abelian varieties, or we could look at abelian varieties together with a point of order n. So what I'll do is I'll look at the moduli space of maps F, like we've been looking at, together with a point where the point has a cycle, is exact period n. And again, modding out by the action of PGL so that we have equivalent dynamical systems identified with one another. As an example, M21 of n, what does that classify? It's just degree 2 rational maps from P1 to itself. So just ratios of quadratic polynomials with a marked point of period n. If I throw away the marked point, I just get a map down to M21, which, as I mentioned before, is the affine plane. So M21 of n is a finite ramified cover of the affine plane. And the dynamical modular curves that I talked about earlier are curves sitting inside M21n because they correspond to polynomials rather than rational maps. So it'd be a rational map where the denominator is just 1. So there's a theorem about moduli spaces of abelian varieties that says if you look at abelian varieties of high enough dimension, the moduli space is of general type. It's the most complicated kind of variety. So here's a pair of conjectures, the first of which is needed for the second. First, that if you take points of high enough period, the moduli space will be irreducible, just have one component. I'm sorry, that should be true for all n. And if you take n big enough, then that variety should be of general type. It should be a very complicated variety. What we know about this conjecture is essentially nothing. I shouldn't say it, it's fragmentary, very few things. So Manus proved that M21, so rational maps of degree 2 on P1, is irreducible for all n greater than or equal to 1. So that's part A of the conjecture for D equals 2, capital N equals 1. Blanc-Conci and Elkes, very special case, proved that degree 2 maps on P1 with a marked point of period 6, that moduli space is of general type. They did that by a fairly explicit and very clever calculation. It's not clear to me whether one could extend that to 7 using current technology of computer algebra systems. So that would be fun. For the dynamical modular curves, a bit more is known, and that was known earlier, because, well, curves are easier than surfaces. So Bush, in his thesis, proved that the dynamical modular curves over C are all irreducible. Patrick Morton used that to give a fairly precise formula for the genus of the curve that in particular shows that it goes to infinity. So the curves do get more complicated. Even deeper and more recently, Doyle and Poonen showed that what's called the gonality of the curve, which is the degree of the smallest map to P1, goes to infinity as n goes to infinity. In some sense, the Doyle-Poonen theorem is a function field proof of the uniform boundedness conjecture for quadratic polynomials. So fairly nice, but again, just for quadratic polynomials. So I've presented to you 3 different topics in arithmetic dynamics, which I hope found interesting and maybe brought to mind some things of yours. What I really want to finish up by saying in the last 20 seconds is that the whole field of arithmetic dynamics kind of came about from taking these very different looking fields and looking for analogies. And it's led to this beautiful theory that's really, even with all that's been done, is really in its infancy. So I want to thank the IMU for inviting me to speak at ICM 2022. I want to thank ICERM for letting me give the talk here in Providence. And I want to thank all of you for your attention.
Hello. So, thank you. Thank you, Joseph. Are you online or are we online?
Yes, we're online.
Okay. So, so thank you for this beautiful lecture, and okay, and maybe you have a last word, or
Yes, thank you for listening. I'm happy to answer questions on the Discord chat if anyone wants to do that. And have a good ICM.
Okay. Thank you. Bye.